So, welcome everybody to the webinar. We are right in time to get started. I saw the participant list going up in the last 2 minutes, so I think we're ready to start in time. Thank you for your interest in this webinar on supply chain optimization using simulation tools. It's a very specific topic, but nevertheless very important these days. On this slide, I'm already introduced, so I would start right away with the webinar. Before I go into the content of the webinar, let me say a few introductory words. First of all, what you can expect for today is how you can optimize the supply chain using simulation, how you can examine dynamic scenarios, for example, ramp up, ramp down scenarios, and what solutions are available on the market. I'm not talking about supply chain strategies in total or in theory, and how to design supply chains. And I will not give you a complete market overview because the market is really big in that. So I will show some very known providers, but not a complete market study. We have 45 minutes today together. The presentation will be around about half an hour, and we will have 10 minutes for Q&A after the webinar. I would like to ask you to ask your questions if you have questions during the session here in the Q&A. Please ask your questions directly, and I will answer it after the webinar. So the raise hand function will be deactivated. Please write down your questions as you have it. We will answer it at the end of the webinar. If you have technical questions or technical issues, please use the chat function. My colleague Bastian Faster will answer your issues directly in the chat. We will record the webinar, so you don't have to take screenshots, and we will upload it on our YouTube channel afterwards. At the end of the webinar, we will also use an online survey tool, which you can use via your browser. I will show you the slide when it's time to use it. So let's start with the content of our webinar. Why is the topic simulation and optimization relevant these days? So we all know the current COVID situation we are facing. And usually we follow this phase model. We also have placed it on our homepage where you can look in all the details. Usually our customers go through each of these phases. Currently, most of our customers are here, planning a recovery, and are back in the ramp up and accelerating ramp up. And then after that, we will have discussions about realigning the strategy. Also rebalancing and redesigning supply chains. And in that discussions, and particularly in the discussions on the strategy and supply chain strategy, this is one field where simulation and optimization can contribute significantly to decision-making, to making best decisions on future supply chain design. So in a few weeks or months, when you have such discussions in your company, please have in mind simulation optimization can help you in making your decisions here. And so I will explain you in the next slides what it means and what is possible using these tools. First of all, 2 slides on the definitions, and so that we have the same image in mind, because the word simulation is used for a large variety of solutions. If you are in a very high level of detail, you're talking about single processes like mold flow or NC programming, very detailed level. Some know also simulation of kinematics, collision checks, for example. A little bit larger when you talk about workstation design, or when you talk about assembly procedures and ergonomics, there's also simulation used for that field. In a more larger scope, we're talking about logistics, material flow, factory design, and production planning control strategies. This is where you can use for material flow simulations. And we talk about whole supply chains, global footprint of distribution networks, and you have a very large scope. You talk about network design. Our focus is using simulation here in that field. That means within a whole production distribution network or within a factory, but not going down to the single workplace. What is simulation? The last definition slide for today. And what is optimization? So I'm talking of two words. Simulation means performing experiments on a model to gain insights into the real system. That means we have a model of the real system and we transfer the insights we gain on the model to the real system. And optimization means finding the best possible solution to a specific problem. So this is what you see out of the definitions. It is very powerful to combine these two methods. Doing a simulation and also combining it with an optimization. How is it technical? Of course, we're talking about simulation runs. What do I need for that? I need, on the one hand, fixed variables. For example, if I want to simulate a factory, I have to model the machine, the personnel, the orders, and so on. These may be fixed variable input variables, and then we have dynamic variables, faults, downtimes, and so on, that follows a certain distribution. This is my simulation model. So I will do a large number of simulation runs. And for example, after a certain number of runs, or if a certain value is reached, then I end the simulation and have a report. This is what we usually do when we talk about simulation. Combining it with an optimization means we have an iteration, like in a control cycle here, where we systematically vary everything we can vary and are allowed to vary to find the best possible solution. For example, if you're talking about a distribution network, where are my hubs, where is my optimal hub, then I would vary the place of the hub, or maybe the size, as long as until I find the best possible solution. So this is the combination of both, very powerful for certain questions, but also relevant for only specific problems. So the first question some might have now is, for what kind of problem do I need such a model and such an optimization? So let's compare it with, let's say, static simulation. Or usually, if I do not, I'm not able, or I don't want to do a dynamic simulation, I, for example, consider only 1, 2, 3 scenarios in a static calculation. So there are some possibilities only such a simulation offers me, and we should look at the advantages in that case. When do I need simulation? On the first part, what I can do, I can investigate unique events or dynamically occurring events and examine the effect over the whole supply chain. For example, what I can model is a plant closure. I can model a failure of a supplier or a plant going down, defective batches, and or changing dates or changing quantities delivered by my suppliers. These are aspects I can model, and I can examine what is the effect over time on my supply chain. This is very important, maybe these days, to examine the robustness of networks in such ramp up, ramp down scenarios. If one plant starts the production earlier than another one and not aligned with the suppliers, these effects are something you can model and examine here. Without simulation, you can calculate scenarios, but you will never see the ramp up, ramp down curve. This is what you see in a simulation. Another advantage, you can compare scenarios under the same conditions. For example, what we see here, if you talk about a production network or a distribution network, and you want to ask yourself, which scenario is more robust? Because what you can easily calculate is a business case, a static business case. That's something you can easily calculate. What is not possible in a static calculation is the robustness. For example, you model a disturbance of 2 weeks. You're running out of parts for 2 weeks. You have a shutdown for 2 weeks. What is the effect? What is the ramp up? What is the ramp down? This is something you can compare for 2 scenarios having this or that footprint. What you can also model, now it's a little bit mathematic, you can examine different distributions of time series because everybody knows a standard deviation, but the standard deviation is not the most common deviation or distribution you find in time series. We have run about 60, 70 different distributions of time series or number series. And what you can examine is in simulations are different distributions of time series. For example, what you can model is a changing call-off behavior of your customers. Also something we see currently, customers are withholding orders, and then you can model the ramp up because then you have a distribution and then the orders will come in all at once. And of course you have to ask yourself, how will my production network react to that? And especially when we talk, for example, about inventory management, optimal inventory management, then you can model different distributions to find the optimum inventory levels. Without simulations, you would use average values and maybe use a safety peak load factor, but this way with simulation is far more accurate. Another advantage, you can consider a lot of scenarios at one time. For example, it is relevant if you talk about a distribution network and you ask yourself what is the perfect location for minimal cost or for a certain target scenario. Without simulation, you would take 2 or 3 points and do the static calculation. With a simulation, you can find simulation-based optimization. You also find on the greenfield the optimal location in theory, and then have a look around what is the next possible realistic option. So you can consider a lot of scenarios. And as I said before, you can calculate more realistic systems. For example, if you talk about dimensioning storage buffer areas or investment alternatives, in the static calculation, you will have a safety factor or a peak load factor. Here you can use the dynamic behavior of the past to calculate what you really need as safety factors. Maybe one example, I had a project with an automotive industry to dimension the buffer for car bodies. And the sequence of the car bodies is a high rack with hundreds of buffers for car bodies, and one buffer place for one body costs around about €3,000 invest. So if you take 10 more, 10 less, it's €30,000, then it's worth an examination instead of just using a peak load factor. And one advantage is that you can consider scenarios without random effects, because you can, as I said, you have a control loop. You can run a lot of scenario runs, and for example, take the average or take the median. So you do not have the danger that you pick one scenario, and especially that one scenario has coincidentally or does coincidentally represent an extreme case that is not realistic. And finally, of course, you have a fast motion simulation, so you can also investigate the long-term effects for example, shutdowns or such events. So a lot of possibilities you take where you can use simulation and simulation-based optimization. Let me give you just 2 case studies and project examples. I think you have ideas in mind where you can use it. These are some project examples. Here it was a company of plant engineering. Here we modeled the whole production distribution footprint with the option of several production sites. And the task was to design the optimal footprint, but not only from a cost perspective, so that not for optimal total cost, but also considering with the robustness and flexibility of the whole network. So they have learned from the crisis 2008-2009 and they put particular emphasis on having short ramp-up curves for breakdowns, on having short delivery times, and in that case also we modeled all the factors that influence cost, and transport, personal invest, and so on. But we also modeled robustness and flexibility of the network and defined criteria for that, and which we examined under realistic conditions. So we took the orders and the OEE values and the mean time to repair values, for example, for bottleneck machines from the past, to model what will happen in the future, and then in the end decided for a scenario which was, from a static perspective, not the scenario with the minimum total cost. So they decided for a scenario that was a little bit more expensive but had a higher flexibility. This is an example for a supply chain. If we go into the factory, another project was in the packaging industry, and it was a material flow examination. So what you see here is the factory model with the conveyor belts, the machine, goods in, goods out, where we evaluated the material flow in the factory, especially because they had complex conveyor lines. They had to invest into new machines, they had to invest into new conveyors, and they asked us what are the optimal buffer areas, which conveyors do we need, and which machine is the best one, because they had several machine options to buy, and they wanted the optimum. And what we did, we collected the data from the past, all the data, process times, lot size, downtimes, and so on. Took the past orders of a year and modeled the behavior under certain scenarios to dimension the buffers and the storages, and to give a recommendation for the investment. In that case, that was really interesting because we also did a static calculation, and after we took the real order data and the real data from the past, we calculated that we needed 30% less investment to conveyor belts in machines than that we compared to the static scenario. So we could significantly reduce the investment. And a side effect for the customer, you see here on the Excel sheets, we built a generic model, so the customer only had to fill out an Excel sheet with input data, how many machines, which properties of the machines, and so on. And we did the simulation run, and the result, and gave the result back to the customer without, and the customer could do it without us, on his own, without having any expertise in simulation. So we built a generic model. He only needs to fill the Excel and click on run, and can use it for similar problems. And also, by the way, for every problem in every plant, for every plant it has the same problem or the same question. So we did a small training, but they did not have to learn the whole simulation environment. Also a side effect for the customer, and he used it after the project also. You saw two screenshots of simulation environments. Here I prepared a short market overview. Of course, it's not a whole market study. It's an overview of relevant vendors and simulation environments on the left side. That is particularly specialized on simulation. Here we have some more general purpose simulation environments where you can simulate, let's say, anything. Anything that has a logic in it, from a factory to a network, or even to a single machine behavior. They are very flexible. And here down you see, let's say, a little bit more focused on production and logistics simulation environments. What you saw on the screenshot for example, in ROI used any logic for the production distribution network simulation, very powerful for the network simulation. And the other one, material flow, was plant simulation by meanwhile Siemens PLM. maybe one explanation where we use that software. Of course, you always have to decide what fits to you, what is a license model that is relevant for you, what are the features you need. In that case, for example, we decided for AnyLogic because only we need the developer license, and if you create a model and give it to the customer can use the model without having to buy a simulation license. So that's a reason why we, for example, use AnyLogic, because our customers don't want to buy a 10,000 euro license just for using a model we created for them. And so it's free to use for the customer what we do for them. That's one strong argument, for example, why we are often using AnyLogic. Also, others have very good advantages. Simulate, for example, is very intuitive, very easy to learn. And so the other ones, everyone has its advantage. What is most powerful if you combine the simulation with an optimization? So having a simulation run is the one hand, but combining it with an optimization is the most powerful combination, as I explained to you. But so you need a second software for the optimization package. You see here some names that are the same. For example, like Siemens PLM, they have the optimization package integrated into their product, and other ones you have to combine. For example, in AnyLogic, you can combine OptiQuest with an interface to do the optimization of the software simulation environment. So sometimes, depending on the solution, you need two softwares. For the mathematics experts, you see also the algorithms that are used in the strategy that is used to do the optimization. Here, OptiQuest most powerful because you have several options from neural networks to the research, and here, of course, more evolution strategies, more rather, let's say, simple optimization. So let's go to the practical application, and let's go into one project. So if you have an idea in mind and say, oh, I have this or that problem and could use simulation for that, let's go through all the steps usually you go through when you do such a project, and let's have a look at what is most important, what are the success factors in these kind of projects. First of all, of course, you start with a problem definition. That means what is the problem you want to examine, and what are the goals and the questions you want to have answered. For example, what is my optimal buffer dimensioning? What is my optimal location for the factory? Or what is my optimal machine combination? These are the goals you have to define here and define the project plan. Then you do the model design. That means you design the model based on the goals and the task. And then you start collecting data. As I said before, for example, when you ask a question, what's an optimal buffer size? Usually we use order and downtime data from the past to do the examination based on what happened in the past. It's simple. It's similar to, by the way, machine learning. You also have a training data set. It's similar here. We do the simulation based on past data to answer your questions. Then you do the model translation. That means you do the coding and create the model. And very important, then you do two steps. That means you verify the model. If no, you have to rework it. That means have I translated it right? And then you do the validation. Validation means is my model able to answer the questions I asked here and to fulfill the goals? So here, did you do the coding right? And here, did you do the right things? If it's not validated, you either have to go back to the model design and change the model, or maybe you have picked the wrong past data or didn't prepare the data right. So maybe you have to collect more data. Often validation is possible, and then you do a test plan. That means how many simulation runs are required and which period of time do you want to examine. You execute the simulation run and analysis. Sometimes it takes a long time, but if you're using cloud services, then you can scale your computing power and fasten and speed it up. Then you have to decide, do you have enough runs? Because you have dynamic influences, so you have to look at the statistics. If it's significant from a statistic perspective, then either if not you have either changed the test plan or do more simulation runs. Then it's the final documentation and reporting and hand it over to you. This is how a project usually goes, sometimes with more, sometimes with less iterations. And maybe just a few tips, what is very important in these kind of projects. First, here in the problem definition, it's very important to formulate all questions. Often happens that you have the questions come up sometimes here, and depending on what the question is, it's more or less effort to answer the question after everything has been done. The same is with a step 2, setting the goals. It's sometimes very costly to change the goals after you have created the model and then go back to the model design to integrate further aspects that had not been considered yet. It is not a question, but sometimes can be very costly. So it's very important to have a very clear understanding of what you want to examine and what is the goal of the simulation study. One lever where you can really save a lot of money and time is a model design. That means you map only the really relevant factors. And this is something I always put emphasis on, because you cannot create a whole digital twin of a factory with all aspects in a feasible time. But it's not always necessary. So it's always depending on the question here, what you have to model and what you can disregard. And you can save a lot of money and time if you map only the really relevant factors. And this is a matter of process expertise, consulting expertise, and experience to get a feeling for that. Because in many projects, the model is too complex for the question, and you have too much effort here because you didn't spend enough time on the model design and asking what is really relevant to simulate. Collecting data. Most important here is to pick a representative data set, time horizon. Enough data, but also representative, because you're based on these past data, you make all the decisions. Yes, in the model translation, finally, and in the verification, it's mainly programming knowledge that is required. Here in the validation, we again, like in the model design, we need the process expertise and the experience. And my personal favorite in these fields, test plan running, simulation runs, analysis, I say it is very important to know how to achieve statistical significance. And I say it again, and I say it again, because this is very important when we talk about dynamic influences and dynamic disturbances. For example, if you model downtimes and having a certain distribution, it's very important to come to statistical significant conclusions. It's the same we're talking about in quality management and in Six Sigma approaches. It's very important to have profound knowledge here. Finally, you get a documentation and a report. And what is quite important here is to document all the assumptions and premises. For example, every assumption you made in the model design, what you disregarded, because if you find out later that the simulation wasn't correct, then it could, the first question, of course, you ask, maybe there are some assumptions we made that we shouldn't have done and we should correct it. So it's very important to document that, as well as finally the code. Of course, if you do some coding and modeling, to document it. This is often something that is disregarded due to budget reasons, but if you want to reuse the model, that's really important to save you time afterwards. So took you through the first project here. Maybe that's interesting for you, and you have some ideas in mind. So let's sum up the most important aspects, what you should take away from our short introduction into simulation and optimization. I showed you some examples in supply chain management, and please keep in mind that in your discussion about supply chain strategy, you can use simulation and optimization as decision support. You can examine everything from a single workplace to whole distribution networks. Very powerful is the coupling or combination of simulation and optimization, especially for complex problems. And it's, of course, mainly relevant for, let's say, costly investment decisions, or where I showed you the scenarios and questions where static scenarios or calculating with average values is not sufficient. Especially in that field, it is relevant. I showed you a short overview on the market of solutions. We also see the market is growing. The tools are also more and more intuitive. And there are many environments you can choose from. In the end, you have to, of course, you can do many mistakes in such a project, but having in mind the success factors will help you surely. And most important is really that you do not only have a look at the programming skills, but also the process expertise when you do a model design and when you do a study, because programming skills are what many people have, but the process expertise is the most critical factor here. So I see 2 minutes before the time, perfect. So you have more time for the Q&A. Before I come to the questions, you wrote down in the chat a few words on the Learning Campus. This webinar was provided by our RI Effiso Learning Campus. We offer the trainings in the fields of lean management, HD, human dynamics, and digitization industry 4.0. This webinar was also one part of our industry 4.0 webinars. And we also have further webinars in the next weeks. First of all, we have further webinars here in the next weeks. You'll see it also on you can register under our homepage here for these webinars, and there will be also further ones. We also have online seminars, by the way, what you see also here, and certification courses. Usually we do it on site, but also as more and more customer demanded it online, we also meanwhile provide online courses. Please ask us if you are interested in anything, or have a look at our homepage. Your contact persons are Typhoon for all our training offers, and for technical questions, please don't hesitate to contact me. Here you have my contact data, and I'm looking forward for any feedback or discussions.